So I've found that when students have to do problems involving the force of tension, they get annoyed maybe more than any other kind of force problem, and we'll talk about why in a minute. So we'll go over some examples involving tension to try to demystify this force, make you more comfortable with finding it so it's not so annoying when you get one of these problems. And at the same time, we'll talk about the misconceptions that a lot of people have about tension so that you don't make those mistakes as well. All right, so to make this a little more clear, what is tension? That's the first good question is, what is this tension? Well, tension is the force exerted by a rope or a string or a cable or any rope-like object. So if you had a box of cheese snacks and we tied a rope to it, so we tie a rope over to here and we figure out how much force do I have to pull with. Since the force is being transmitted through a rope, we'd call that tension. So, it's a force just like any other force. I'm going to call this T1 because we're going to add more ropes in a minute. So it's a force exerted just like any other force. You treat it just like any other force. It just is a force that happens to be transmitted by a rope. So what's happening here in this rope? Ropes are typically composed of fibers that have been braided together or wound around each other so that when I exert a force at this end, right, when I exert a force down here on this end, I pull on this end of the rope, that force gets transmitted through the rope all the way to this other end and it'll exert a force on this box. And the way that works is I pull on the fibers here, they're braided around each other. So these fibers will now pull on these fibers here, which pull on the fibers here. And this could be parts of the same fiber, but the same idea holds. Once this force is exerted here, it pulls on the ones behind them, keeps pulling on the ones behind them. Eventually that force gets transmitted all the way to this other end. And so if I pull on this end with a force, this end gets pulled with a force. So tension is useful. Ropes are useful because they allow us to transmit a force over some large distance. And so what you might hear, a typical problem might say this. A typical problem might say, all right, so let's say there's a force of tension on this box and it causes the box to accelerate with some acceleration A0. And the question might say, how much tension is required in order to accelerate this box of mass M with this acceleration A0? What tension is required for that? Now, a lot of the problems will say, assuming the rope is massless. And you might be like, what? First of all, how can you have a massless rope? Second of all, why would you ever want one? Well, the reason physics problems say that a lot of times is because imagine if the rope was not massless. Imagine the rope is heavy, very massive, one of those thick, massive ropes. Well, then these fibers here at this end would not only have to be pulling the box, they'd also be pulling all of the rope in between them. So they'd have to be pulling all this heavy rope in between them, whereas the fibers right here would have to be pulling this amount of rope, half of it, right? The fibers here would have to be pulling this amount of rope, which is heavy, not as heavy as all of the rope, and the box. And then, so the tension here would be a little less than the tension at this end. And then the tension over at this end, well, these fibers would only be pulling the box. They don't have to pull any heavy rope behind them. So since they're not dragging any heavy rope behind them, the tension over here would be less than the tension over here. You'd have a tension gradient or a varying amount of tension where the tension is big at this end, smaller, 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 smaller. That's complicated. We don't want to have to deal with that. Most of these physics problems don't want to have to deal with that. So what we say is that the rope is massless, but we don't really mean the rope is massless. The rope's got to be made out of something. What we mean is that the rope's mass is negligible. It's small compared to any mass here, so that even though there is some small variation within this rope of the tension, it really doesn't matter much. In other words, maybe the tension at this end is 50 newtons, and the tension at this end is like 49.9998. So, okay, yeah, they're a little different. The tension here is a little greater, but it's insignificant. That's what we're saying. So let's try to do this problem. Let's get rid of that. Let me get rid of all of this. And let's ask, what is this required tension right here in order to pull this box with an acceleration of A0? So to do these problems, we're going to draw a force diagram the way you draw any force diagram. You draw the forces on the object. So we're going to say that the force of gravity is equal to mg. Force of gravity is wonderful. Force of gravity has its own formula, mg. I just plug right in and I get the force of gravity. And if you're near the earth, there's always a force of gravity pulling down. Since this box is in contact with the floor, there's going to be a normal force because the floor is a surface, the box is a surface. When two surfaces are in contact, you'll have this normal force. And then you're going to have this tension. Here's the first big misconception. People look at this line of this rope and they say, well, it looks like an arrow pushing that way. So they think that this rope's pushing on this box, and that doesn't make any sense. You can't push with a rope. If you don't believe me, Go right now. Go pause this video, tie a rope to something and try to push on it, and you'll realize, oh yeah, if I try that, the rope just goes slack and I can't really push. But you can pull on things with a rope. Ropes cause this tension, which is a pulling force. Tension's a pulling force because this rope gets taut, it gets tight, and now I can pull on things. Normal force is a pushing force, right? Forces, the two surfaces push on each other. The ground pushes out to keep the box out of the ground. But ropes, tension is a pulling force. So I have to draw this force this way. So this tension T1 in my force diagram would point to the right. I'd call this T1. Those are all my forces. I could have friction here, but let's say this cheese snack manufacturing plant has made transporting their cheese snacks as efficient as possible. They've made a frictionless ground, and if that sounds unbelievable, maybe there's ball bearings under here to prevent there from being basically any friction. We'll just keep it simple to start. We'll make it more complicated here in a minute, but let's just keep this simple to start. Now, how do I solve for tension? The reason people don't like solving for tension, I think, is because tension doesn't have a nice formula like gravity. Look at gravity's formula. Force of gravity is just mg. You can just find it right away. It's so nice. But to find the force of tension, there's no corresponding formula that's like T equals and then something analogous to mg. The way you find tension in almost all problems is by using Newton's second law. So Newton's second law says that the acceleration equals the net force over the mass. Now, if you don't like Newton's second law, that's probably why you don't like solving for tension, because this is what you have to do to find the tension, since there's no formula dedicated to just tension itself. So what's the acceleration? Well, I have to pick a direction first. So do I want to treat the vertical direction or the horizontal direction? I'm going to treat the horizontal direction because my tension that I want to find is in the horizontal direction. So my acceleration in this horizontal direction is A0. That's going to equal my net force, and in the x direction I only have one force. I've got this tension force. So the only force I have is T1 in the x direction. And since that point's right, and I'm going to consider rightward as positive, I'm going to call this positive T1, even though that's pretty much implied, but positive because it points to the right, and I'm going to assume rightward is positive. You could call leftward positive if you really wanted to. It'd be kind of weird in this case. Now I divide by the mass. I can solve for T1 now. So I just do a little algebra. I get that T1, the tension in this first rope right here, is going to equal the mass times whatever the acceleration of this box is that we're causing with this rope. So don't draw acceleration as a force. This is a no-no. People try to draw this sometimes. Acceleration is not a force. Acceleration is caused by a force. Acceleration itself is not a force, so don't ever draw that. Okay, so we found tension. Not too bad, but this is probably the easiest imaginable tension problem you could ever come up with. So let's step it up. You're probably going to face problems that are more difficult than this. Let's say we made it harder. Let's say over here someone's pulling on this side with another rope. So let's say there's another T2. So people are fighting over these cheese snacks. People are hungry. And someone's pulling on this end. What would that change? Let's say this person over here is like, you're not going to get my cheese snacks. Say they pull with a force to maintain this acceleration to be the same. Right? They're going to pull whatever they need to, even with this new force here, so that the acceleration just remains A0 to the right. What would that change up here in my calculation? Well, in my force diagram, I've got another force, but I don't draw this force pushing on the box. Again, you can't push with tension. You can only pull with tension. So this rope can pull to the left. So I'm going to draw that as T2. And how do I include that here? Well, that's a force to the left. So I'd subtract it because leftward forces we're going to consider negative. And now I do my algebra. I multiply both sides by m to get ma, but then I have to add T2 to both sides. And this makes sense. If I'm going to pull over here, if I want my T1 to compensate and make it so that this box still accelerates with A0, even though these people over here are pulling to the left, this tension has to increase in order to maintain the same acceleration to the right. And let's step it up even more. Let's say war's about to break out over these cheese snacks right here. So let's say someone pulls this way. Someone pulls that way with a force T3. So we'll call this T3. Someone's pulling at an angle this time. Let's say this force is at an angle theta. Now what does that change? Again, let's say this T1 has to be such that you get the same acceleration. What would that change up here? You're going to have a tension force up and to the right in my force diagram. So you get a tension force this way. This is T3 at an angle theta. Now I can't plug all of T3 into this formula. This formula was just for the horizontal direction. So I have to plug only the horizontal component of this T3 force. So this component right here. Only that component of T3 do I plug in. I'm going to call that T3x. T3x is what I plug in up here. T3y, this isn't going to get plugged into this formula at all. The T3y does not affect the horizontal acceleration. It'll only affect the vertical acceleration and maybe any forces that are exerted vertically. So I'll call this T3y. How do I find T3x? I have to use trigonometry. The way you find components of these vectors is always trigonometry. So I'm going to say cosine theta, and I'm going to use cosine because I know this side, T3x, is adjacent to this angle that I'm given. So since it's adjacent to the angle I'm given, I use cosine because the definition of cosine is adjacent over hypotenuse. And my adjacent side is T3x. My hypotenuse is this side here, which is the entire tension, T3. So if this tension was like 50 newtons at an angle of 30 degrees, I couldn't plug the whole 50 newtons in here. I'd say that 50 newtons times, if I solve this for T3x, I get T3x equals, so I'm going to multiply both sides by T3, so that would be like our 50 newtons. So T3, the entire magnitude of the tension force, times the cosine theta, whatever that theta is. If it was 30 degrees, I'd plug in 30 degrees. This is what I can plug in up here. So now I can plug this into my Newton's second law. I couldn't plug the whole force in because the entire force was not in the x direction. The entire force was composed of this vertical and horizontal component, and the vertical component does not affect the acceleration in the horizontal direction, only the horizontal component of this tension, which is this amount. So if I plug this in up here, I'll put a plus, because this horizontal component points to the right, plus T3 times cosine theta. And again, the way I'd solve for T1 is I'd multiply both sides by m. So I'd get ma naught, and then I'd add T2 to both sides, and then I'd have to subtract T3 cosine theta from both sides in order to solve for this algebraically. And this makes sense. My tension T1 doesn't have to be as big anymore because it's got a force helping it pull to the right. There's someone on its side pulling to the right, so it doesn't have to exert as much force. That's why this ends up subtracting up here. T1 decreases if you give it a helper force to pull in the same direction that it's pulling. So conceptually, that's why this tension might increase or decrease. That's how you would deal with it if there were forces involved. You can keep adding forces here, even friction. If you had a frictional force to the left, you would just have to include that as a force up here. You'd keep doing it using Newton's second law and then solve algebraically for the tension that you wanted to find. So to recap, remember the way you solve for tension is by using Newton's second law, carefully getting all the signs right and doing your algebra to solve for that tension that you want to find. Also, remember the force of tension is not a pushing force. The force of tension is a pulling force. You can pull with a rope, but you can't push with a rope. And in this problem, the tension throughout the rope was the same because we assumed that either the rope was massless or the mass of the rope was so insignificant compared to the mass of this box that any variation didn't matter. And in other words, the tension at every point in this rope was the same, and that could have made a difference because if we were asking the question, how hard does this person over here have to pull on this rope to cause this acceleration? If the rope itself was massive, this person would have to not only pull on this massive box, but also on this massive rope, and there'd be a variation in tension here that honestly we often don't want to have to deal with. So we assume the rope is massless, and then we could just assume that whatever force this person pulls with, because tension's a pulling force, is also transmitted here undiluted. If this person pulled with 50 newtons, then this point on the rope would also pull on the box with 50 newtons.